All right, let's take a few seconds. It's one of those periods I'm going to stop you. I stop you, you stop working, right? All right, there we go. On that note, if I could please have Diana, why Excel? Yeah, why? Why do we use it? Why do we care about it? What does it do for us? What makes it a valuable tool? It's a good way to organize data. Yeah. There's been a lot of different types of software that have been developed for data management. And there's a lot of spreadsheets that are developed. Spreadsheets tend to, at least for the sciences, be one of the easiest ways in which we can organize things. There are still some people that like to write out their science in longhand and then transcribe it. I would discourage you going forward from doing that. I would encourage you to always record your data electronically as much as possible. If you cannot, it's fine. But one of the biggest sources of measurement error, if you remember the two types of error we talked about, was measurement and process. Measurement is those things that you can control. Process is those type of errors that reflect other variables that are influencing the system. One of the biggest sources of measurement error is transcription errors, transcribing things from one format to another. One of the reasons that I do all my data collection electronically. What is the big, oh dear God, con of that approach, Jordan? I just gave you advice and I'm telling you why it sucks. Now you tell me why it sucks. So you got to learn, and that's actually one of the great things, since you guys are scientists, that's what we do. I mean, I really don't use anything from when I was a student. Now, mind you, that was over 30 years ago. But the reality is it's constantly. And Sean and I were playing around with some stuff today based on how I taught you 5 years ago, 4 years ago. Really? Damn. And the big point of it is what we're doing today is radically, fundamentally different than what I was teaching Sean just a few years ago, because everything constantly is changing and there are better ways of doing things and easier ways of doing things and updated ways of doing things. So what you guys will learn this semester is sort of the best of our knowledge now in terms of data management, data analysis, data processing, with the expectation that it's going to continue changing. I was writing a peer review for an article last night where if it was published maybe 3 years ago, I'd be like, yeah, it's pretty cool. And I lit into it really hard to the editor because of how out of touch and how out of date it was. Now, to the writers, I think I was much more cordial, and I hope I was. We'll find out. If you see some random people crying somewhere further west of us, then no, I wasn't as nice as I think it was. But data management. One of the major problems with recording everything electronically is you can lose it. It's one of the reasons that you always want to back up in multiple different places, and you do be attentive to that. But transcription errors are huge. Excel allows us to manage data, process data, organize data. We don't use it very often to actually do anything with the data. It is really about organization and management. Great. As I mentioned, one of the things that's available to you all, if you get geeky and you just sort of want to know, there's a lot of stuff Excel can do. I've taught you a very small little piece of it in this exercise, but these videos go through a lot more additional shortcuts, little ways of going around. That's how I learned most of my stuff. I took a lot of stats classes. I never took a class in R, ever. Well, really wasn't much around, as you'll discover, but it's just something that you build off of. So a few things with this data management. Where's the formula bar for that? I'm going to Lucy. I can't see what I'm writing, so maybe I'll put glasses on. Okay. Cool. Okay, so now I would like Loren to correct that. What Lucy told us was fantastic, but there were a few things that we didn't want to do. I do. We're going to be doing this all semester long. You're going to be correcting me. I'm going to be correcting you. We're going to be correcting each other. This is going to be a mantra of this class. It is a never-ending festival of corrections. So did we want to do that here? Is that cool? In cell B2? Why? What happened in cell B2? What did we lose? That makes us sad. We lost the variable name, so we don't know what the variable name is. So I'm just going to do Command Z because whenever you screw up, it's not a big deal. You just go back. Now we're done. If you're using a Windows-based machine, it's Control Z. It's your favorite key on your keyboard. Command Z, Control Z, because we make mistakes all the time. Who cares? You fix it. So what's the first thing I should do, Loren? We did sort of bottom. Okay, so I go down to bottom. This make me happy. Does it? How would I know? How would I know? Madison, how would I know? I'm very lost. Why? What is that category? I was expecting, what is that variable? I did too. Maybe, I don't know. I don't know. So Connor, I don't know what's going on in column B. Fix it? Restop row. All right, so now, Emmanuel, what do I do in B52? B52 or B62? You made me very happy for a second because this past weekend we were listening to Rock Lobster, which is B52s. And then I realized it's not B52, it's B62, and now I'm sad. Emmanuel, what do I do now? Emmanuel, why do I hit equals? What is the whole point of equals? Brings you to a format. Oh, I like that. I like that. So what am I going to do now? One of the nice things, and fortunately R is going to do this for you as well. It's going to give you suggestions based on what it thinks you're trying to do. So as you start to write it out, notice we get a bunch of different functions going to come up. You don't have to necessarily know what they are. If you know what you want and we want average, it pops in, you can just use that. Now what do I do, buddy? Which one requires you to think? Yeah, memorizing what the cells are. Stop thinking about things that don't deserve your thought. There's a lot of stuff that's really complex. We're going to pay attention. We're going to think about those. You guys are going to do a model next Tuesday that is going to piss you off and make me very happy. It is awesome. It's a very cool little model, and you can't play, Connor. You're the only one. Sean's going to be leading it. It's awesome. There's a lot of thinking that we'll be doing. In those places we don't have to think, let's not think. So how can we avoid thinking? Click and drag. But what I like to do is I like to use arrow keys and shift keys. So what I did there, just so you watch that, I go to the cell I want to begin in. I hold shift on my computer because it's a Mac. I hold command and then I hit up arrow and that will go to the end of the series. I continue holding shift and I go down arrow 1 and now I have my cells. It's a nice little thing. Makes life very fast. Makes life a little bit easier. What do I do? How would you stop? All right, great. Now I'm lazy. I am lazy and I want the averages of everything. So this will be the last thing that we do on this particular rodeo. Catherine, I'm lazy. I want the averages for all 4 variables, but I want to do this as easily as possible. You can. If you highlight the cell of interest and you put your cursor down the bottom right-hand side, your cursor goes from a white cross to a black cross. At that point, you can hold down your mouse and with your second finger, you drag it across and voila. Okay, I have to do one little fix. What do I have to fix, Catherine? Delete it. And because Excel is relative, it will automatically calculate the average for each of those individual columns. Now, this came up before, and it was a really good observation. Notice that this calculation includes a bunch of cells that are empty. Is that okay? Or are we mistaken? Do we have a problem? Should we be crying at this point in panic and terror? We're fine. Why? Because they're empty. What would happen if we put zeros in for all those values? It would change the average because 0 is a data point. It would totally change what we got. It's empty, you're good. Go ahead and keep going. And Nick, I did record it, but you forgot. Okay, ladies and gentlemen, I know I just let you go, but I'm stopping you again because we get to actually one of the most important concepts in the type of statistics that we'll be doing this semester with. And sort of, let's call them introductory statistics. Well, remember what we are using is we are using Popperian statistics. And Popperian statistics is based on the concept of nulls and alternatives, and then how we will go about evaluating those. So one of the things, and there's not a lot that you have to know, and you have to be able to just know it, not think through it. Most of the class, we'll be able to think through things, but there's a few small things you just have to know. One of them is null, one of them is alternative, what those mean. Not in a case-by-case situation, what they always mean. And one of them is, what is Popperian statistics doing for us? Because that's going to inform all the stuff that we actually work with. So let's start with the null. So what is a null hypothesis? For that, I want to go with Chandler. So you have an easy time. You can just read the answer this time because the next person is going to have the harder part of that. Yeah, the null hypothesis is always, it is always this, but the pattern is random. There's always a pattern. It's whether the pattern is random or non-random. So the second, I'm going to say easy question goes to Seth in this regard. If the null hypothesis is random, then what's a null hypothesis that compares the biodiversity of transient insects at these cabbage palms versus resident insects at these cabbage palms? And by the way, these data come from those plants directly behind you in the windows. You know? So what is the null hypothesis for the biodiversity of insects that fly between plants versus insects that just stay at the plant? There's no pattern. Another way of saying is there's no difference. Since we're comparing the actual numbers, you could say there's no difference. There is no pattern. It's completely appropriate. If you want to be proactive, you're not a negative nanny. You could say the pattern is random. All those say the exact same thing. Does that make sense? Amanda, you had your hand? Okay, so now this is the little trick of the question. Victoria, what does that mean? What does that mean? There could be things influencing it. That's a fair statement. But the test, Amanda, go ahead. Yes, they're essentially the same. The test variable is not influencing it. There could be things influencing biodiversity of these insects at these trees, absolutely, 100%. But the test variable is not influencing it if we find support for the null hypothesis. And that's another thing. We find support for hypotheses. We do not reject hypotheses. I know technically we will fail to reject a null hypothesis. That's the language, but we're going to get in the idea of we find evidence for patterns. The pattern might be random, the pattern might be non-random. Does that make sense? If you flip a coin, simple, little, quarter, and I am now mentally flipping a coin in my head. You guys can see it flip up. I catch a coin, I put the coin down. What's the probability it's a head or a tail? 50-50. 50-50. If I flip it again, put it down, what's the probability it's a head or a tail? 50-50. If I flip it again, put it down, what's the probability it's a head or a tail? 50-50. What if I got 3 heads in a row? Is it still 50-50? Absolutely, it's still 50-50. Oh, and by the way, I know I said I cheat all the time. This time I'm being honest. I take an honest coin, I flip it again, boom, flip it down. It's a head again. Is it still 50-50? Absolutely, I do it again, still a head again. Still 50-50? Yeah, it's still 50-50. The probability of seeing that individual occurrence 5 heads in a row is small, but it's still random. What we're trying to do with statistics, we're trying to evaluate that random pattern versus a non-random pattern. When we do Popperian statistics, we are evaluating the null hypothesis. It's one of the reasons you have to understand the null. The null always means the same thing. The pattern is random. That's what the null means. Now you will translate that into a number of different ways. The null hypothesis that there is no difference. That's perfect. That's so random. The whole hypothesis is no correlation. That's exactly what you guys got in your pre-survey when we compared your intuition versus your test score. Your intuition was all over the map and there was no relationship to your overall test score. If you felt that you had a lot of statistical intuition, that had no influence of whether you passed that little mini test or not. If you felt deeply insecure about your statistical intuition, that had no bearing of whether you got a good score on that test or not. There was no relationship whatsoever. There was a random pattern. Make sense? Good with that? It's very important to know that statement. Therefore, surely, what is the alternative? And you get the easy one. You get to read first. Joey? Joey, yep, Julie, yep. Alternative. Bingo. The alternative hypothesis just says that there's a non-random pattern. That's what it's saying. It's a non-random pattern. The null, random, like flipping a coin. The alternative, non-random. The test variable is having an influence. So that could have many different forms. Maybe we say there is a correlation. Maybe we say that there is association. Maybe we say that there is a difference. What would be a good alternative hypothesis for this study? Comparing resident and transient arthropods at these trees. And Jeffrey? Yep. Resident and transient. Yep, love it. Yeah, there is a pattern. In this case, you can even define what that pattern is. There is a difference. So now here's the kicker. Whenever you look at the measure of the average, is there going to be a difference? Mathematically, 100% all the time. What these are evaluating is whether that's a random difference or a non-random difference. Whenever you calculate averages of two groups, there will be a difference. Every once in a while, no, but really, honestly, give me God. Yes, there's always a difference. It's helping you discriminate whether there's a real difference or a non-real difference. And this is the basis of Bayesian or Popperian statistics. The null hypothesis is the foundational principle of one of these two philosophies. Does someone remember which one? How about someone named Haley? Sure. It's this concept of null hypothesis and alternative hypothesis. Is that Popperian or Bayesian? As Popperian. Popperian has some weird things. For one, Popperian has this weird concept of null hypothesis and alternative hypothesis. It's useful, but it's weird. How many people, when you first learned about alternative and null hypotheses, you're like, yeah, that makes sense. But when you heard about p-values, you go, duh, let's move on. Sure, that's what happens. It's a weird concept. It is a useful concept, and we will find value in use in it. But do recognize it is weird. We are doing Popperian statistics. Popperian statistics evaluate null hypotheses. Null hypotheses describe random patterns. Therefore, Popperian statistics evaluates whether the pattern is random or not. If it's random, you describe it. There's no difference. Or resident and transient appear to be the same. If you reject the null hypothesis, we end up describing the alternative. There is a difference. Or maybe we notice that one of the averages is much larger than the other, and we describe it. Resident biodiversity is much higher than transient biodiversity. And by the way, I don't know mathematically off the top of my head which one it was. Does that make sense? Okay, keep going. I'm going to stop you pretty soon again to get to p-value, but keep going for now. Ladies and gentlemen, I'm going to be stealing y'all for a bit. Again, as I said before, these will be topics that we will address multiple times throughout the semester. But it is always a good idea to start getting your head around them as we go through them. And one of the things we had to do is use Excel to run statistical tests. Now, running a test in Excel is just, well, it's dumb, but it works. And when I started, it was the only free way of doing it. And I don't want to spend my money on running tests. I would like to spend my money on other things. Fortunately, they came up with R, and we'll talk about all the beautiful things that are starting on Friday, Thursday. But for right now, we're going to use Excel. And I ask you all to run a t-test. And there are some very nice little things about Excel. So first part, you probably have this computer on your computer at this point, but there's an analysis tool. You open up and you load the analysis tool back on your computer. That creates a little add-in, and that add-in can run some very simple basic statistics. So sometimes if you get on a computer that doesn't have R on it already, this is just a nice little way of doing it. Or if you just don't want to deal with any coding for a moment, you do a quick little snappy thing and get some information very fast. So it's nice. So we go to data analysis. And now I need to know from Dominique, what test do I want to run? 2 sample t-tests, where there's a lot of them, Dominique. And I'll read them out to you because they're really tiny. This one is a 2-sample paired 2-sample of means. This is a 2-sample assuming equal variances. And this is a 2-sample assuming unequal variances. Okay. One of the things that we're also going to get very comfortable with and very used to is there are a lot of assumptions. Most of the assumptions will get you to the same basic endpoint. So here's the annoying part about it. Most of the assumptions that we will spend a lot of time worrying about are not going to change your overall understanding of the information. But we will pursue the appropriate test based on the correct assumptions so that we kind of align the same degree of rigor you would do with your science with the same degree of rigor that you should do your analyses. These are important considerations. And when you do consider the assumptions, you tend to have a better understanding of what you're getting and why you're getting the information that you are. So there'll be a few times when we're talking about assumptions where you'll just be annoyed. That's all right. Just let me work with you for the long term, and we'll get at a good point of why we do them and what we get out of them and why it's important to consider them. Seth? We're going to do unequal because we were just told to. And by the way, we should be doing unequal variances because if you look at your variances like standard deviation, were they basically the same number or were they pretty different? I don't have the screen in front of me. You guys do. You guys calculate it. The standard deviations, are they pretty close to the same or are they pretty different? Give me the numbers. Oh, they're the same. Yeah, because they're the same. So let's do equal. Nice thing about equal is it actually makes some of our statistics easier to understand. Unequal gets really weird. We'll explain that later. All right, so we do equal variances. Thank you for calling me out. Thank you for correcting the situation. And then we pick our ranges. So we pick one range. We pick a second range. Do our ranges have to be equal in size? And I do apologize, I can't make this any larger. So we have a hypothesized mean difference. Sometimes your null hypothesis is not zero. Sometimes your null hypothesis might be a non-zero number. In this case, our null hypothesis is zero. Mathematically, we expect a random pattern when there is no difference between the means. So our null hypothesis is, x1 minus x2 equals 0. We can leave it blank because that's what it assumes. Our level is basically describing our p-value. We run it. It opens up to a new worksheet. Something did not work out right. Oh, we have labels. I forgot to check that. We now run it. We get up here. We get that. And we get this. Pretty cool? Okay, how many people are really happy when they saw this? Lorraine was like, yeah. Anyone just see, that's a lot of numbers. I don't know what the hell I'm supposed to look at. Yep, that's fair. One of the nice things about R is R tends to give you the information you need, not all the extras. You can call out the extras easily. One of the things about most other statistical operations, they give you everything when you only want some things. Okay, there are a few numbers that we need to know when we are doing the statistics, and we'll go through these later. But one of the things that I'll do if I'm working in Excel is I will highlight them. And highlight the numbers that I need to know. We need to know our P to TLP. We need to know our degrees of freedom. We need to know our means. I actually forgot a number. We need to know our t-stat. We need to know those. I'll mention it very briefly right now. We'll go into more detail later. The relationship between this number, our t statistic, and our degrees of freedom, that is what calculates your p-value. The relationship between these two numbers is what defines your p-value. So when we report statistics, we tend to report our test statistic, in this case it's a t-stat, our degree of freedom, which describes a measure of your sample size, and our p-value. We record all three of those sets of numbers. Okay, we'll go through those details later. But we do have interesting information now as we have our p-value. So Dominique, we're going to start with this. I actually already called you Gil. We're going to start on this. Is that a large or a small p-value? It's very small. 1.4 times 10 to the negative 20. Gil, if you were going to round that number, what would you round it to? I would. It is 0. And one of the things with stats is stats work on an asymptote, so you can never literally hit 0. You basically start to hit an approximation of 0, and that's what we did here, 1.4 times 10 to the negative 20. It is a small number. The p-value is used to evaluate the null hypothesis. If the p-value is large, then we describe the null hypothesis. If the p-value is small, then technically we reject the null hypothesis, but really what we do is we describe the alternative. That's what we do. If the p-value is small, we describe the alternative hypothesis. If the p-value is large, we describe the null hypothesis. That is take-home Popperian Statistics 101. You guys are done. You get that concept. The rest of it is actually just operational. So Gil told us this p-value is small. Right now, don't worry about two-tail, one-tail. We could go through those later, but this is small. So which hypothesis are we going to describe? The null or the alternative? We're going to describe the alternative. The reason is the p-value tells you the probability of making a mistake by rejecting the null hypothesis. It tells you the probability you've made a mistake if you reject the null hypothesis. What is the probability we've made a mistake if we reject the null hypothesis? 0%. There's no chance we're making a mistake by rejecting the null hypothesis. If you reject the null hypothesis, what do you have left over? You have the alternative. That's why we describe the alternative. That is how stats operates. That is the logic behind Popperian statistic. You evaluate the null. If you cannot reject the null, you just describe it. Cool. If you can reject the null, you just describe the alternative. Cool. So at this point in time, Gabrielle, is there a difference or not between the biodiversity of arthropods for residents versus transients? Yes. Where's our evidence? Our p-value is the evidence. There is a difference, not because of those numbers up there. There's a difference because we have the evidence right here. Now, here's a trick, Gabrielle. Which group had a higher biodiversity, residents or transients? Resident had a biodiversity of 0.15. Transient had a biodiversity of 0.92. Which one's larger? Transient. So once you know there is a difference, we know there's a difference because that's a small p-value. So we reject a null. You reject a null, you just describe the alternative. We know there's a difference. Now you go use this information. Now you go look at figures, you use means and averages, and you describe that difference. So there's a difference. Now, we're going to play a little game. I want a person to give me a good biological sentence to describe that pattern. And this time, I'm not just going to call you out randomly. I'm going to let someone give a shot at it. Who wants to give me a good biological sentence that describes that pattern? You may not, and you may not, and you may not. So 3 people that I've already eliminated from this game. Who would like to play first? Do I have a marker? Do you have a marker? Sean, do you got a marker? Who would like to go up? I could call random. Manuel, come on, give me some. I'm pretty okay with that. So there is a difference. Keep going, I gotta hear it again. Okay, if I just make that a little abbreviation and right? Is that what I got? Is that what I get? Then give you the next information. Start with the t-stat. Start with the t-stat. You do not need to worry about positive or negative because that all just depends on which is the first set of numbers, which is the second set of numbers. So you can just take the absolute value of that. You know, just because we made transient second, it ends up being a negative number because transient was larger. But if we made transient first, it would have been a positive number because transient, thank you, Siri, because transient's larger. All right, so we can just start that. How many decimal points do you need? Yeah, really, stop at one. It just does not matter. All right, so give me the next part, Manuel. I want DF. 87. Now I want someone to explain why we put down the test statistic and the DF before we describe the P. And this one's open to anybody. Really? More, but no, nope. No, Gabrielle. Bingo. Because these two numbers are what we use in the calculus, literally calculus, by the way. I'm not using calculus to be euphemistic. I am saying calculus because it's a bloody curve. And it's the relationship between those two numbers based on a normal distribution that gives you that p-value. No. What do? Are we always going to be in this class? Oh, hell no. No. Okay, and then what do I do? Emmanuel? Okay, by the way, p-value equals 1.4 times 10 to the negative 20. Is that a large number or a small number? Is that a real small number, like a stupid small number? Like, do we really care how many negative values there are and how large a negative exponent there is? No. So I would encourage you, once you get to this point, just do p is less than 0.001. Just after that does not matter. It's 0. Any point after that, it's 0. You're fine. You're fine. Connor? Nah, because then you're cheating. They're trying to make something look more significant. Notice I use just the word significant by itself, which I consider almost like a cuss word, you know, and you're trying to game the system.
Like if it's like your percentage, so it wasn't just like it was above that.
So let's say you had a p-value of 0.049 versus a p-value of 0.002. Which one of them is much closer to that threshold? 0.9, but you could put down technically p is less than 0.05 in both cases, which makes it seem like it's the same effect size, same strength, and that's game in the system. Yeah, so it's only when we get down to the zero, which I would encourage us. Now, how many people like this sentence? How many people would be able to tell their grandmother exactly what you found? And your grandmother would be like, yeah, that's cool. What do we not like about it? It's a good sentence, by the way. It's actually much better than most people do in the first round. But we're going to make it better. We're going to make it sexier. Though it's really good to begin with. Most people really don't do that. No. How many people had a sentence like this? How many people had a sentence along the lines of, based on the p-value, we were able to reject the null hypothesis. Therefore, there was no random pattern between the two groups. Anyone? How many people mentioned null hypothesis in their sentence? How many people mentioned p-value in their sentence? How many people use the word significance in their sentence? Cool. I like the fact that a lot of people did, but very few people put their hands up. Yeah, you have these eyebrow twitches when I said different things, which gave me an indicator, maybe so. Yeah. Are we statisticians or biologists? We are biologists. Let's always be biologists. Stats is a tool. We're going to use stats to understand biology, speak biology. Is this statement true? Is it clear? No, what do we not know based on this statement? We don't know which one's larger. Do we know based on our data which one's larger? Should we not say which one's larger? Can we say which one's larger? In fact, let me start that. Can we say which one's larger? Oh, hell yeah. Why can we say which one's larger? Our p-value. It's tiny. Saying there's a difference. And now that we know there's a difference, can we use the means to define which one's larger? 100%. Which one's larger? Where do we see more biodiversity? Which group? Transient. So someone give me a nice, simple sentence you could tell your father, your uncle, that would make that point. No stats. I just want language. Amanda. Perfect. I love it. That's a really good, solid statistical sentence. The biodiversity of transient arthropods was higher than resident arthropods, or exactly as I thought I heard Amanda correct me. There was more biodiversity in transient arthropods than resident arthropods. Perfect. Love it. And then put down the information. When you guys write this next sentence, I'm looking for good biology. A good biological statement with statistical evidence. Questions? So I'm just going to erase this one we have now. But I'm going to also leave it erased. You guys keep going. Okay, ladies and gentlemen, it's going to be the last time that I stop you today. And real quickly, I want to talk about figure legends. People get these confused. One of the reasons I went a little bit off the rail last night with this manuscript I was reading is people get these confused. Figure legends are going to accomplish one of two outcomes depending on where you are sharing the figure. For the most part, in this class, we're going to treat figure legends the way you would for a poster and or presentation and or a publication in something like Nature or Science. We're going to treat them as result statements. Now, if you can think of doing a poster, you don't have a lot of real estate, right? So you have very, very little space to use to communicate information. If you're writing a figure legend like you would in terms of a lab report or a paper, Your figure ledger would provide total information so it could stand by itself, but wouldn't describe anything. In a poster, that takes up a lot of space. You would still have to, in a poster or a presentation, give your overall statement about the result and therefore take up more space. So for posters, presentations, and some journals, Science and Nature being two examples, figure legends tend to be result statements. They describe the pattern, whether the pattern is random, whether the pattern is non-random. They describe the pattern. That's the way we're going to be teaching you here for the most part, because all undergraduates, you guys are going to be doing presentations as part of your senior research, and all the graduates, you guys will be going to conferences and doing presentations and all different variety of things, including your final defense, where you're going to provide this information. Any advice we give you in this class, Sean and I give you in this class, if your faculty look at you and like, no, that's dumb, who do you listen to? Carefully think. Not us. Listen to your faculty. In the class, you give us what we asked for, but if your faculty tell you they want a particular way for doing your poster, doing your presentation, giving your talk, you do it that way. Always do it that way. But we're giving you sort of suggestions and advice for here. So when you are asked to do it, and I'm looking out here the figure where you're doing it for the dog habituation, write it as a result statement. Write exactly as you guys had up here. There was higher biodiversity of transient arthropods than resident arthropods. Then you give the evidence. Now for here, we have to give the means because we don't have anything else. Do you have to give the means or the medians when you have a figure? No, your figure is literally your evidence. And therefore you don't have to put that extra information. You can certainly, but you definitely do not have to. When you are writing a figure legend for a normal lab report, normal paper, or a manuscript, what do the figure legends have to look like then? Nick? They're more descriptive. They should be understandable by itself without having to look at the paper to make sense of it. For a manuscript, more often than not, there is no result part of it. There's no description of the pattern. It's a description literally of the figure. So a good example of that type of figure legend for the dog habituation would be the amount of time it took dogs at the Gulf Coast Humane Shelter, Fort Myers, Florida, to habituate to different child-specific behaviors. That would be the figure legend for paper. For the class, though, we're going to ask you to be doing results because it's a utility that everyone will be using in this class, regardless of anything else we're going to do. Anything make sense with that? Okay, we're going to stick around. If you have any questions, stick on by, continue working. If you're done for the day, you're done for the day. On Thursday, we're going to start with R. And then after maybe a half hour to 45 minutes of talking about R, we're going to switch over and work on the Excel. If you are done, you leave after the R. If you're not done, use the entire time. If you want to work independently, but we will be here during that time for anyone who has any questions. Make sense? Any other last question or comment for today? Okay, have fun.